Okay, in this lesson I'm going to talk about some of the features of LTI systems that make them special. So LTI systems stand for linear and time invariant systems. First of all, why would we care so much about linear time invariant systems? Well, for one thing, many physical systems are time invariant. Okay, because they just, let's say a response of a spring to some motion, or the the response of a circuit to an input. It's not going to matter at what absolute time that input came, it's going to respond the same way. And that's what it means to be time invariant. On the other hand, linear is a bit more of a stretch. When you talk about systems you would encounter in the real world, well, there are also systems that we design, so I guess we could design a signal processing system to be linear and time invariant by choice, and that often is the case because we know so much about how to design such systems, because the math that we're going to see in a moment works out so nicely. But even physical systems that you encounter, if you want to analyze them, they may not be linear, but if they're not, you may linearize. And that simply means to use the Taylor series approximation of your system. So if your system is being used within some narrow operating region, even though it's nonlinear, it may look mostly linear around the region it's being operated. So, again, because the math is so convenient for LTI systems, then it's often the case that a real system that's nonlinear is linearized, so you can then analyze it this way. So we're going to assume a system is both linear and time invariant, and the magic is, once we do that, there's something very important. The impulse response becomes very meaningful. So let's talk about what the impulse response is. So the impulse response says you have your system H, it's linear time invariant. You put in a delta function, that's the impulse function, and you see what comes out. And we're going to just give this the label little h of t, and h of t is the impulse response. Okay, so because it's what the system did when you put an impulse function in. So actually, maybe it's best if we have a little picture of what we mean. Here's t, here's time 0. We put a delta function in, and what comes out is something like this. Who knows what comes out? And that is the impulse response. You just knock your system at time 0 and see what comes out. Now, if the system was not linear time invariant, this wouldn't be very meaningful, because if you put an impulse function in at a different point in time, you might get something completely different out. Or if you put an impulse function with a different magnitude, and it wasn't a linear time invariant system, you might get something completely different out. Okay, but being LTI means that in fact this characterizes your entire system. So from this, we know the output of any input. We know h of a general x of t. Okay, and that's the magic. So why do we know that? Well, let's check here. We're going to use linear and time invariance to see what happens. So we're going to represent x of t, or let's do continuous time and discrete time. So start with discrete time, which is what I have done in your Piazza notes. I have this whole lesson in the Piazza notes. So xn is, now you can, very intuitively, you could see that you could represent it. Any discrete time signal is just a sequence of delta functions, right? It's just a sequence of values. Each one could be represented by a delta function. So we'll say x of k, the value at time k, times a delta function at that time. All right, so that's very intuitive. Now, in continuous time, representing it as a sequence of, it's no longer a sequence, but as a group of delta functions is a little more abstract. Okay, I'll write down the formula here. Negative infinity to infinity. Okay, so again, we put the delta function right at time tau. We have it at height x of tau. Now, but it's a little more abstract that we're splitting up our x of t into like a bunch of these delta functions. However, notice that both of these, all I've really done here is I've rewritten the sifting rule. So if you have trouble believing that this works, just think back to the sifting rule, and this is just a restatement of the sifting rule, right? Because again, for the sifting rule, if you have a delta function at time n, remember k is our variable in the sum, so this is a delta function at time n, then we just take the value of the function here. Okay, so we recognize that by the sifting rule, you just plug it, you just get x evaluated at time n here, or x evaluated at time t here. Okay, so this is a valid equation. Now we'll plug it into the our system formula. So we know what comes out is going to be h operating on, I'm going to do the continuous time case here because I did discrete time in the Piazza notes. So h operating on an input x of t can be rewritten using the substitution above as it operating on this integral. So this is just a restatement of x of t. And now we're going to use the fact that h is a linear system. Now integration is linear as well. It's like a big sum. So that means we can bring the integral out. And furthermore, t is our time variable for our signal. So, well, I'll do it in 2 steps here. So I can do x of tau delta t minus tau. And then integrate the result. Okay, so now I'm going to use linearity again to bring this x of tau out. Okay, so let's do this. Integral comes out. X of tau comes out. This is by linearity. X of tau is just within this integral. Tau is a variable. This is a signal that's a time signal, t, and we're saying let our system h operate on this signal. It has a constant x of tau multiplied by the signal, which is a delta function. Okay, so we need to figure out what does the system h do to that delta function. Well, first of all, because x of tau is just a scaling parameter on that delta function, it can come out by linearity. And we get x of tau, and we get h operating only on the delta function. And then lastly, we say, well, what's h going to do to a delta? Well, we know by the definition of the impulse response that if I put a delta times 0, I get h of t out. And by time invariance, I know that if I put t delta delayed to time tau, I should get that same impulse response delayed to time tau. So it's delayed by tau. All right, and there we have that now the response to any input x is just the convolution between x of t and the impulse response h of t. So voila, the impulse response is in fact completely characterizing what our system does, because once we know the impulse response, we know what it will do to any input. It's going to do a convolution. All right, so convolution was introduced just as a mathematical quantity, and now we're saying, in fact, convolutions go hand in hand with LTI systems. Any convolution can be thought of as an LTI system, and an LTI system just does convolution. So it's pretty typical, if you have an LTI system, to draw in the block diagram. You, instead of saying system H, you say this is a convolution with H of t. That's what this system does. Okay, so in comes x of t, out comes x of t convolved with h of t.